In this excursion, we want to explain RSA. RSA was already mentioned in different places as a very popular two-key encryption method. And here, it's not necessary for understanding, but it's good who wants to have a feeling. Here we want to compute an example to understand how this RSA is working. RSA is really the most popular two-key encryption system. It is widely used, was developed 1977, and RSA is simply the initials of the names of the inventors, Ron Rivest, Adi Shamir, and Leonard Edelman. Rivest and Shamir, famous computer scientists, which design hash value. Adi Shamir is more the crypt analyst. Ron Rivest is more the encryption method designer. I mentioned already all the two-key encryption systems are based on a difficult mathematical problem. And the mathematical problem RSA is based on is the factorization of very large numbers. And the observation is if one has a really huge number with hundreds of digits, then it's very difficult to find out whether this number is a prime number or whether this number is a product of different prime numbers. So if the numbers to be checked are long enough, then in a realistic time frame, it is impossible to answer these questions. So the solution cannot solved practically. This is the idea which makes such a procedure secure, because to break RSA, one needs to be able to solve this mathematical problem. One needs to be able to factorize huge numbers. So the installation, the product of two very large randomly chosen primes, cannot be factored in a realistic time frame without knowing the two prime factors. Now I want to give a numerical example of an RSA encryption, and of course the method works with huge numbers. Here an example I can illustrate it only with small numbers. So what is the starting point? The starting point are these two prime numbers. These two prime numbers which are chosen by the sender, and then the factor, the two prime numbers are multiplied to each other to get the composite number. So here in our case, we take the two prime numbers 17, p equals 17, q 31, and calculate their product. Calculate the number, the composite number computed out of the two prime numbers. In this case, it's a very simple and small number. It's 527, and this is equal to 17 times 31. Then, in the next step, we have to calculate a special mathematical functions, the so-called Euler phi function. In case when a number is a product of two prime numbers, this Euler phi function can be computed very simply, because the Euler phi function of a prime number equals to the prime number minus 1. So to compute the prime number of n, the Euler phi function of n, we have to compute simply p minus 1 times q minus 1, and in our case, p is 17, q is 13, so we can compute the Euler function phi of our composite number n simply by multiplying 16 and 30, and the result is 48. By the way, with other numbers, it's much more difficult to compute the Euler phi function, but in that case, it's easy. Now, next step, This is to install what we need. Now we have to generate key pairs for participants. So let's compute a key pair for a participant A. Idea is select a number. Select a number that is smaller than phi of n, smaller than the Euler phi function, and which is prime to the Euler phi function. That means there is no common factor, only one. In our case, it was this 400 something, so in our case we choose e equal to 13, and then we can take this number, 13, and 527 as a public key of A. This 527, this was the n. Yeah, this was here the n, you remember that. Now we have to compute the corresponding private key. And to this end, we calculate the multiplicative inverse d to e with respect to the phi of n. That means a number that is multiplied with e, a number d that's multiplied with d, modulo phi of n equal to 1. So, and when we do this in our simple example, d equal to 37 has this property, since e times d, since 13, this was e, times 37, modulo the Eulersche phi function of n, this was 480, that's equal to 1. So by means of this computation, we get the pair 37, 527 as a private key of A. So we have chosen the public key, and by means of this computation, computing the multiplicative inverse, we get the private key of A. And exactly here you see the problem. To compute this multiplicative inverse becomes simple if one knows the both prime factors p and q. And it's very difficult if it's almost impossible to compute if the product of p and q is a very big number. So we stay here with our small numbers to understand the RSA method. What we need at the end are only these three numbers, ed and n. So the public key is e and n, the private key is d and n. And now we can apply our RSA method. We can apply our RSA method to message. So let's consider the encryption and the decryption with the public key or with the private key. So it's encrypt with the public, decrypt with the private key to have this. So we take a message, and the RSA method, the message of course is considered a number. We can encode it in a number. It's a dual string, and dual string stands for a number. And the the encryption of that message can be computed taking the number message consists of up to the e and then modulo n. This is the encryption, and of course the decryption consists if one takes the cipher up to d modulo n, then one gets back the message. So you see with the e, this was a e and n, this was a public key, we can encrypt the message, and by means of d and n we can decrypt the message. In case we want to compute the digital signature, then we have to encode the message, this was a hash of the message, by means of the private key up to d, so that everyone can verify the digital signature by means of the public key. I show this here. The message takes the message, takes a private key, for example, for creating a signature to the up to D modulo n, and then to decrypt, to verify the signature, one has to take cipher up to E. I repeat, message ciphers every time are considered in that case as numbers. Now we want to apply this method and show how we can use it sending a message. So we have our communication partner B, and B wants send A the message 456. Remember, we consider messages, we encode messages as numbers, so I have taken a very small message, the number which corresponds to the number 456. What is B doing? B wants to encode this message so that A is able to read it. So what B is doing, B is taking the public key from A, this was the 13527, and use this to encrypt the message 456. Encryption is easy by computing 456 to E modulo n, and if you compute this, the cipher of 456 is 447. This cipher is sent over the open internet to A. A gets this, and A applies his private key. Private key, dn was 37537, and now computes, takes the cipher up to D, up to 37, modulo 527, and A gets back the original message, which was this 456. The correctness of the RSA method is based on a well-known number theoretic theorem. This is a famous Fermat's little theorem. And this theorem says that for any A and any number A and any prime P, the result of A to P minus 1 is equivalent to 1 modulo P. And this is true in all cases when A is not a multiple of P. And the argument is that if it is true that E times D is equivalent to 1 modulo P minus 1 Q minus 1, then there exists also in X with E times D minus 1, which is equal to X times P minus 1, Q minus 1. So RSR is very famous, most popular to key encryption. And here in this excursion, you could see how RSA is working, and you could also see why it's so popular, because the computation is difficult, but the scheme of the computation is very simple.